chemistry time.
Is that like a requirement?
No, I want to do it so that you have access to it. Well, hopefully this isn't too poppy. I don't know. We'll have to just see, and maybe I'll just use my own dollars to buy a new lavalier mic if this one fails me. We're talking about chemistry, period. No, JK, chemistry of solutions is what we're going to call this. Chemistry of solutions. Chemistry of solutions. What is a solution, you might ask yourself? I'm waiting for you to not only ask yourself that, but then also answer it. What is a solution? Oh heavens, haven't we done the vocab? I'm going to come over and interview Hayes about it with my... Oh, hold on, Deli. Let me...
Is it a homogeneous mixture?
Yes. Yes! You can say yes into it without the popping because yes doesn't have a popping consonant. Thank you, Dali Anders. Let's clap. Not you. Not you. Anyway, a solution is a homogeneous mixture, which we've talked about before in chemistry and in physical science. What's homogeneous mean?
Like all, no, like you can't tell the parts.
Yeah, you can't tell the differences between the parts. Hot. What's a solution made out of? I don't mean specifically, because a solution can be made out of millions of different things. But a solution must be made out of what? What are the parts of a solution called? A solute is dissolved. And a solvent, which I usually put does the dissolving. I don't love that. That's not very good English, but the thing I would rather put is just dissolves. Like it is what dissolves it. But if I put dissolves, then you could get confused very easily. So a solute is dissolved. The solvent does the dissolving. What's this? No, it's not a box. What's it supposed to be, probably? A beaker. It's supposed to be a beaker. What's this?
A line, a water line.
Water.
Solution.
This will say is a solution of H2O and NaCl. What's NaCl?
Salt.
Table salt. It's one kind of salt, specifically table salt. What kind of salt is it? Sodium chloride. So what is the solute? The table salt is the solute. What is the solvent?
Water.
Water. Okay, good.
Dissolving.
That's what's dissolving it. Good, good.
I don't see how people
What can we measure? What can we measure about, I don't either. What can we measure about a solution? Yeah, how much is dissolved, which we call what? How much what is dissolved? How much solute is dissolved divided by either the total solution or the amount of solvent. And we call this quantity what? Yes, sometimes. That's one way we can measure, but in general, this quantity is called what it is. My example, yeah, concentrated is what I was looking for. The example, I'm going to try to show this to the camera. Look in there, camera. I can see it focus up on there. Look in there, camera. Look in there, YouTube viewers. It's not urine. Let me tell you, none of this is urine, but it really does look like it. Since I poured this out of my tea kettle, hold on, I'm going to go grab my tea kettle too. Doot, doot, doot. Since I poured it out of my tea kettle, here's the tea kettle. Since I poured it out of here about 10 minutes ago and the tea bags are still in it, what's probably more concentrated? This tea in my cup or this tea in the kettle? Probably the tea in the kettle. So what if we were telling this to second graders, we probably wouldn't use the word concentrated. We would say it's water. Not water. What is it? This is what-er than this. Mm-hmm. Yeah, you'd probably just say stronger. So we could even say the strength of the solution, but the scientific way is to call it concentration. And we have several different ways of measuring this mathematically. The best one, in my opinion, because when you use a word like best, you're necessarily talking about an opinion. The best one, in my opinion, is abbreviated capital italicized M, which is molarity. And molarity equals moles of solute per liter of solution. So as an actual equation, it is amount over volume. I should probably have done it this way, where capital M, capitalized italicized M is molarity, which we measure in molar. It's just another capital italicized M. N is amount, measured in what? What? Moles. And capital V is volume, measured in liters. Yeah, you could measure it in milliliters, but it wouldn't give you, the unit wouldn't be molars, which is, it's technically moles per liter, but we abbreviate capital M molar. What's going to happen if you have, as many of your problems do, what's going to happen if it gives you, for instance in this, let's say I dissolved 5.1 grams of sodium chloride in a liter of water. Well, can we still use this? What am I going to have to do first? If my given is 5.1 grams of sodium chloride, I have to use a conversion, as you say. I have to convert it from grams of sodium chloride to moles of sodium chloride. So it works in this. And then I divide it by the liters of the solute? No. The liters of solvent? No. The liters of solution. The whole thing, solution. Liters of solution. This is the best way, in my opinion, to measure concentration, but you should know some other ones. Another way of measuring concentration is percent by mass. There's another one called percent by volume. Percent by mass is mass of solute over mass of solution times 100%. You've worked with percentages a lot before, right? This is the same calculation as when you get a 60 out of 75 on a test. You just divide the amount you got divided by the total amount of the test times 100%. And the same thing with volume, except for in this case we use liters of solute divided by liters of solution. Do these have to be in liters? No, what do you notice about the units here? They're matching. They could be literally anything. You could use Daly's left eyeball size of solute divided by Daly's left eyeball size of solution. As long as the units match, it makes absolutely no difference. It can be a made-up unit even, because we're dividing that by that. That's not true for molarity. I'm saying that for the percent mass and percent volume. As long as they're the same unit, it doesn't make any difference at all what unit you use. We do usually use grams for solute and solution for the mass, and we use liters for the volume one, but it doesn't have to be that way. And then, kind of like molarity, and this is an easy way to get confused, so be careful. Kind of like molarity, I'm going to do this in a different color. We also have a thing called molality, which is different in two ways. So this was molarity. This is molality. Why did they name them so similar to each other so that the babies would get confused? It's so that the babies would get confused. Good. Molality, to make it even more confusing, is a lowercase m. Molarity was capital M. Molality is lowercase m equals the moles of the solute divided by the kilograms of not the solution but the solvent. So molality is N over lowercase m. That even confuses you too. Do you understand the differences between molality and molarity? First of all, what's the difference in abbreviation? Yeah, molality is lowercase and molarity is uppercase. What's the difference in calculation? Well, instead of using moles divided by liters in molarity, we're using moles divided by kilograms in molality. And what's the other difference? Well, the other difference is instead of dividing by liters of solution, which is both together, we're dividing by kilograms of just the solvent, okay? Do you have questions about any of those things? The final common way of measuring concentration is mole fraction. We don't use, this is on your test, but we don't use it in the lab very much. I'm going to look in my book. What? Oh, the dilution equation. We will, but that's not a measure of concentration. We will talk about it, though. Yes, thank you. sub A equals N sub A over NA plus N, oops, lowercase n, B. What's X probably stand for? X is, make a guess. What are we calculating here? It is a way of calculating concentration. No, we have a name for this that I could title it here, but it's going to be the same thing. It's mole fraction. Mole fraction. X is mole fraction. In this case, oops, fraction. Boy, that's ugly looking. In this case, it's A to B. The mole fraction in A as a part of the whole thing. N is amount measured in moles. So then A is substance A, which can be either the solute or the solvent, and B likewise is substance B. Both measured in, well, these are not measures really, they're just telling us, those are subscripts that tell us which amount we have. So basically, the mole fraction of A to B is just the mole fraction of A plus the mole fraction of B divided into the mole fraction, or the moles of A. I misspoke somewhere in there, but if you plug and check, you'll be okay. What unit will this have? I put in parentheses A to B where I normally put the units, but what units will it have? No, mole over mole, which is no unit. No unit's a fraction. I have an itch in my eye. What does that mean? Eyelash cancer, probably. Not appropriate. I'm going to have to cut the video now. Okay, next we're going to talk about, we are going to talk about your dilution equation next, but do you have questions about any of this? Here, I'll get my microphone and put it in your face if you have a question. Do you?
No.
Okay, perfect. 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 Now we'll be able to check the pop, 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 pop. Can I erase any of this? Oh yeah, I'll not erase the title. So write down this next thing while I'm talking about it, but before I write it, because I'm still doing some erasing. The dilution equation, already, what do you think it's going to be about? What does dilution mean? What would it mean if I diluted my tea? Yeah, I would make it less concentrated. Dilute is kind of the opposite of concentrated. In fact, qualitatively in the lab, we have a lot of solutions that we either call dilute if they're not concentrated, or, okay, I'll fix it, or concentrated if they are concentrated. In fact, if we say concentrated, we usually mean it's 100% that thing, or as close to 100% as we can get. For instance, the hydrochloric acid that's in the lab that we call concentrated is really about a 35% solution, but it's as concentrated as it can physically get, because if you try to put more hydrogen chloride in it, you drop your marker on the ground. No, if you try to put more hydrogen chloride in it, it bubbles out as a gas. So that's as concentrated as it can possibly get, so we call that concentrated. Anyway, the dilution equation is M1 V1 equals M2 V2. Pretty simple equation. There's another way we can write it that, let me make sure that. We also sometimes, we usually use 1 as the starter concentration. Like just, we can sometimes call it M0 V0 equals MF VF, which would just be initial and final. But the one your book uses is M1 V1 equals M2 V2. And all we do, just like when we did our gas laws, are we ever going to use this equation as such? We'll always have to do what? We'll always have to manipulate, because we're never solving for the quantity M1, V1. We always want to solve either for M1 or M2 or V1 or V2. Let's do a practice problem of one of these. We can do practice problems of the other ones too. I want to do this one on camera. It says, what volume of a 3 molar potassium iodide stock solution would you use to make a 0.3 liters of a 1.25 molar potassium iodide solution? So our givens are molarity 1 equals 3.0 molar potassium iodide. Molarity 2, volume 1. What am I? Actually, I'm trying to find volume 1. So molarity 2, yeah, I was right the first time, is 1.25 molar potassium iodide. And then V2 is 0.300 liters. Okay, what should I do first? I have my givens written out. Hold on, my find is V1. I'm trying to find how much of the first solution, how much of the 3 molar solution I'm trying to find. So manipulate first. What do I do? Tell me what to write, Skylar. What? I'm trying to. Okay, so V1 equals M2 V2 over M1. Okay, next step, Dally. Tell me what to write. Molar.
Yeah, what?
And potassium iodide, but you don't have to write that for this, or maybe I don't write it for this. V2, it's all the same thing. V2. Molar. Molar, just like the things near to. And then V1 equals math. Meanwhile, while you guys are doing your math, I'm going to blow my nose into the microphone. What is that? Let's see what that sounds like. We have a lot of interesting stuff to learn about now that the pop protector's gone. Well, what do you think?
Why didn't you think I could take it off?
Well, probably when I took my microphone off, like I slid it through my shirt, the little pop protector stayed there, and then somewhere where I walked, it probably fell out. What do you got? 0.125 what? Liters. Yeah, so that means the answer tells us is that we would use 0.125 liters, which is 125 milliliters, and we would take our 3 molar solution, pour in 0.125 liters of that, and then fill up the rest with water, enough to make 0.30 liters. And that would dilute it. Does that make sense? Okay. Okay. Does that answer your question, Natalie, about the dilution equation? I think you already did that in your chapter review, but thank you for asking it for your friends. And we did. And is that satisfactory to you? Okay. Okay. The next thing we're going to talk about is the process of dissolving. The process of dissolving. What did you notice in your lab happened when you dissolved? Well, please focus up, camera. What did you notice in your lab happened when you dissolved calcium chloride? Yeah, what was it? Specifically, what changed in temperature?
Was that the first one or second one?
The calcium chloride.
I think it was colder.
Warmer, yeah. So sometimes there can be an energy of dissolution. Energy of dissolution. In fact, I think that always there's an energy of dissolution. If something dissolves, there's always an energy of dissolution. It's just that sometimes we notice it more, like for instance in the calcium chloride, than we do other times. The energy of dissolution is an amount of heat released or absorbed as solution occurs. What does it feel like if the energy is released? Yeah. It feels hot. What does it feel like if the energy is absorbed? Cold. What can we do to make something dissolve faster? You do this all the time without even thinking about it. Mix. Okay, so 3 ways to improve, let's say, expedite. What's that word mean? What's expedite mean? Hi, Mr. Levercheck, how do you do? What's the word expedite mean? What if you go on Amazon and ask for expedited shipping on your... Fast, make it faster. 3 ways to expedite dissolution. What are they? Hayes said 1. Yes, stirring. We group stirring and shaking into agitation. What's another way? Yeah, you did this. But tell me what the other ones are. Here's a hint.
temperature?
Do you,
Increased temperature?
yeah, okay, fine. I was going to give you a hint, and it was going to be a good one. Increased temperature. My good hint was going to be if... Okay, give me a second. My hint was going to be... I'm holding up for the camera. My hint was going to be if I try to make this with cold water, eventually the tea would look like this, but it wouldn't be after 20 minutes. It might take 2 or 3 days. You ever make sun tea?
Yeah, it takes a minute.
It takes a minute. It does take like all day because you're warming it up with the sun instead of on the stove or with the boiling water, whatever you normally do. But if you try to make, like I sometimes do, I like to sometimes call it icebox tea because refrigerator tea makes it sound like it's a flavor of tea that tastes like your refrigerator. But I make it for like 3 days so the tea will get strong enough because the temperature is not as high as the tea is, I guess, produced to be.
So you don't make, so like we boil water.
Hold on, let me get you on the microphone. Yeah.
No, we boil the water and then we put it over the tea bag and then put it
Yeah,
in the thing and
yeah.
it still comes.
Yeah. What Dally was trying to say before she neglected to speak on camera was that she boils the water first and then puts it over the tea bag, which is probably the right way to do it, but it is a whole other step that if you just are willing to spend 3 days passively, exactly. I'm the only one in my house that drinks it though, so if I am patient, I can wait 3 days for my tea to save myself doing the extra 5 minutes of boiling the water. Anyway, increase temp, and then the third one, as Skylar rightly says, is increase surface area. What's the example of this? Yes? Yeah, so what would be an example of that? Like, give me an example of, okay. Hold on, Hayes. Your example's not great, but let's put it on camera anyway. There you go, Hayes.
So you take your little pot and you put your water in it and it fills it up, but it doesn't boil fast enough for you. So you get the biggest pot you can find and throw all the water in it, and it all dissolves really quick.
Yeah. So what he's saying is, and that's a fine example. You're talking more about like cross-sectional area than surface area, but the example that comes up in earth science a lot is that if we have the mineral calcite, which can dissolve in water, if we have a block of calcite, it would take longer than if you have powdered or ground up calcite. Or the other classic example is like a sugar cube will take longer to dissolve than the same mass of just powdered sugar or even granulated sugar. Yes, of course, yeah. Hayes, you can watch this video to see what's going on. We can have different amounts of the kind of not quite a qualitative, but no, not quite qualitative. But one way that we can measure, one way that we can measure, I'm trying to do something. One way that we can measure the strength of a solution is whether it's unsaturated. What's that probably mean?
Not saturated.
Not saturated. Good. Saturated, which we'll talk about, and then supersaturated. What does it mean if you're saturated? Like if you are, we talk about this in church all the time. Sometimes people say that you are saturated in culture. In our church this comes up, that someone is saturated in culture. What does that mean?
They're in it.
They're not just in it, but they're completely full of it.
Yeah.
Completely full. If I was to, how could I tell when my tea has become saturated with tea?
It gets darker.
Yeah, when it's as dark as it could possibly be. When there's so much tea that the water literally cannot, we use the verb hold, I'm putting in quotes, it cannot hold any more tea. What if I pour some salt into water, even while it's boiling, eventually I'll go to a point where I cannot get any more salt to go in there. All of it will fall out of solution. So that point is called saturation, when it's holding as much as it can. What does this imply then? Unsaturated would be? No. Less than it can hold. Here, it means what? The what? It is the less than what can hold? The solution. Unsaturated is less than the solution can hold. Saturated is as much as it can hold. What does supersaturated mean then? More than it can hold. More than it can hold. What does that mean? All of these imply at a given temperature. For instance, if it's saturated at a cold temperature and we warm it up, it would be unsaturated. But if we make it saturated and then cool it down, it's actually supersaturated. It stays in solution, but it's technically holding more than it should be able to hold at that temperature, and if we give it a seed crystal or even a little shake, it'll all fall out of solution. Not all, but enough of it will fall out of solution that it's only saturated and not super saturated anymore. And we'll do an example of that in the lab. You can watch really cool YouTube videos of it too. So these are kind of not quite qualitative, girls, these are not quite qualitative measures of solution. We can measure saturation, but we can also use them qualitatively. So they're kind of either qualitative or quantitative ways of measuring whether a solution is at its max capacity, basically. Questions about that? Okay, the final thing we're going to talk about, I'll leave those bottom stuffs on there for a while so that you can keep writing them down. The final thing we're going to talk about is colligative properties of solutions. Colligative properties of solutions. Get out of the way. Colligative properties of solutions. These are properties of a solution that depend not on what is dissolved, but how much of it there is. Properties arising from amount dissolved. Not what it is that's dissolved, but the amount that's dissolved. The colligative properties that we talk about commonly are vapor pressure lowering, osmotic pressure lowering, I think. Uh-oh, I lost my page and now I look like an idiot. No, it just says osmotic pressure. And then what we rarely talk about those, or at least they're in your book, and you properties arising from amount dissolved. Properties arising from amount dissolved. The two we most commonly talk about, though, are boiling point elevation. I'm going to give you an equation for this too. Boiling point elevation and freezing point depression. Okay. Boiling point. What's the boiling point? Let's break this down. Break it down. What's boiling point?
When it boils.
Yeah, it's the temperature at which a substance boils at under a given pressure. What would it mean for the boiling point to be elevated?
It gets bigger.
It gets bigger. What's the normal boiling point of pure water? Do you know? In Celsius? Nope, that's the freezing point. 100 degrees Celsius is the boiling point, the normal boiling point of pure water.
It's elevated to be 100.
Yeah, so what that means is that as we add stuff in it, the boiling point goes up. It elevates. The boiling point goes up. What does that imply about the freezing point? As we add stuff, the freezing point goes down. When might this be handy? I can think of one specific example in the kitchen.
Temperature. When we want to increase the temperature.
Okay, when would I want to increase the temperature of something and I could use dissolving salt in water to increase the boiling point of my water? When you're trying to make some dang, any kind of pasta, but mac and cheese, yeah, you put salt in it, and people think, the salt is going to make it taste yummy, and it is, and that's one of the reasons you use salt. But another reason is also it makes the boiling point higher, so then when the water actually boils, it's at a higher temperature, and the noodles can cook faster. Boiling point elevation. When would this one come in handy? When would freezing point depression come in handy? When would I ever want to mix some kind of solute into my frozen water, maybe ice or snow, to make it so it's not frozen anymore? Put some salt in it? Probably not if you're going to ingest the water, no. But what else do you do with ice and snow? I know. What else do you want to do with ice and snow that you can't do because they're ice and snow and they're slippery?
Oh, roads.
Yeah, walk on them or drive on them. And then you put the dude from the Department of Roads is spreading salt or a salt. It's probably not sodium chloride, and we'll talk about why. But he's spreading some kind of salt, something that'll dissolve on the road so that the freezing point gets lower. So now it's 20 degrees outside. Obviously, 20 degrees Fahrenheit outside, which is about negative 10 Celsius outside. So the water is frozen, right? If there is water, it is frozen on the road. Now he spreads some solution on it, and the freezing point of the water is now 15 degrees Fahrenheit. Well, now the water's not frozen anymore because its freezing point has been lowered. Here are the equations, and we'll do math for these, but for boiling point elevation is this. Delta T sub B equals I. This is supposed to be like a little fancy Latin letter I. Ah! Little fancy Latin letter I. Capital K sub B, lowercase m. From the internet, your book is wrong. I'm going to tell you about it in a second here. And then for freezing points depression, it is delta T sub F. Delta T sub F equals little I, little fancy Latin I, K sub F, lowercase m. Where in both of these, delta T is what?
Change in boiling point.
Change in temperature. For boiling point, it's T sub B. For freezing point, it's T sub F. What should, based on our conceptual things from a second ago, what should the answer for the boiling point elevation equation be? As far as should it be positive or negative?
Positive.
It should be positive because it's boiling point elevation. It makes it go up. What should the freezing point one always end up being? Negative. Good. Little fancy I is the Van Hoff factor, which we'll talk about. Leave some spaces because we'll talk about that. And then K sub whatever. Yeah, VAN apostrophe T space HOFF. And then leave some spaces because we'll talk more about that. Hoff, H-O-F-F.
Yep. And then what's
Factor. And then the capital K is the molal, either freezing point depression or boiling point elevation constant. And then M, lowercase m, is molality. Be careful that it's molality and not molarity. Molality. Molality is measured in kilograms, moles per kilogram. The molal freezing point depression or boiling point elevation constant is measured in degrees Celsius per molal. It could also be Kelvin per molal. And then the change in temperature is degrees Celsius, and the Van Hoff factor is unitless. The Van Hoff factor is what we need to talk about more specifically. The Van Hoff factor is an integer, unitless integer, equal to the number of species evolved in solution. What that means is that, for instance, if I have sodium chloride, NaCl, and I dissolve it, it breaks up into sodium ion, Na+, and chloride ion, Cl-. Okay? So it developed two species, two separate things. So for sodium chloride, the Van Hoff factor is 2. For calcium chloride, CaCl2, we get Ca2+ and 2Cl-. So the Van Hoff factor is 3 because it's 1 plus 2. Okay? For anything covalent, like sugar or gasoline, for anything covalent, it's always 1.
Okay, we used to do that countless.
Unitless, integer. Integer means it has to be a whole number. Is the number of species evolved equal to the number of species evolved in solution? So when it dissolves, how many species does it turn into? How many does it separate? Only ionic separates. And when it separates, is it 2 like sodium chloride? Is it 3 like calcium chloride? It could be more. Aluminum oxide would be 5. I don't even know if aluminum oxide is dissolved, so don't at me. Don't at me. Don't at me. Bye.